All right, let's do it a little harder one here. 92 is a good question here. It says here we have a heart defibrillator that passes 10 amps through a patient's torso for 5 milliseconds in an attempt to restore normal beating of the heart. And then A is how much charge passes through. So current is charge over time. That's what current is. It's the rate. So the amount of charge would be current multiplied by time. So if we got 10 amps and we multiply it by the 5 milliseconds, and then let me just watch my units here. Here's 10. And an amp, remember, is a coulomb per second. And then I'll go 5 times 10 to the minus 3 for milliseconds. So that seconds will cancel, and I'll be left with units of coulomb, which is good, because that's what I'm being asked for, charge. And then 10 times 5 is 50 times 10 to the minus 3. I suppose we could write that as 5 times 10 to the minus 2 coulombs. I suppose we could even write that as 0.0500 coulombs also. All right, so 0.05 coulombs is, or 50 times 10 to the minus 3, or 50 millicoulombs would be the answer for A. How much charge is it? Now, B says what voltage was applied if 500 joules of energy is delivered. Okay, so remember, power is current times the voltage. And we are asked for the voltage. We were told the current, and we're not directly told the power, but remember, power is energy over time. So I'll replace this as the energy over time, current times voltage, and these three I know. I know the current, I know the energy delivered, I know the time delivered, and now I can solve for voltage. So I'll start with the energy. What was this? 500 joules in a time period of 5 milliseconds. Okay. In fact, maybe I'll even just do this math right here, because 5 goes into 5. I can think of this as 5 times 10 to the minus 2. Okay, because 5 goes into 5, 1. That's nice. And then bring this upstairs, and I've got 10 to the 5 watts. So 1 times 10 to the 5 watts is the power delivered for that small amount of time. It sounds really big, like a lot of power, but remember, it's only for a short amount of time. So it's only, well, it's still 500 joules of energy. It's a pretty good shock to your system. So I can see why this is a defibrillator. Going to make your whole body tense up and hopefully shock it back into rhythm. Okay, now the current, as we read earlier up here in this problem, is 10 amps. And so I'll put a amp here for our 10 amps. And we're looking here for volts. So I'll divide by 10. So that becomes 1 times 10 to the 4. And then I have a watt divided by an amp. And we might remember that a watt is an amp times a volt. And if that's the case, you can see that the amps cancel and it's just voltage. But you could also remember that a watt is a joule per second, and an amp is a coulomb per second. And so when you cancel out the second and bring the coulomb over, you got a joule per coulomb, and that's the definition of a volt. So the potential is, looks like this is 10,000 volts. And so there's B. C says, what was the pass resistance? Okay, so using Ohm's law, V over R, or rewriting it as R equals V over I. Again, I've got this 10,000 volts, and I've got a current of 10 amps. So that leaves me with 1,000. And remember, the definition of an ohm is a volt per amp. So it's like the resistance is 1,000 ohms. Okay. And then D sounds like it goes back to last semester. It says, find the temperature increase caused in an 8 kilogram of the affected tissue. So This sounds like a specific heat type of problem, where when you give it a certain amount of energy, which we said back here in B is 500 joules. And if we remember the specific heat, well, maybe I should just do the mass, because they said what the part of the body that is being affected, so maybe like across the chest as you're using the defibrillator, this would be 8 kilograms. 8.0 kilograms. And they don't explicitly say, but I'm going to take the human tissue to be mostly water. I guess I'm a little tempted to go all the way back into that chapter, because I remember there was a big chart and they gave the specific heats of human tissue. Let's see if I can find it kind of quickly. Oh no, I don't have the book here and the PDF. Let me finish the solution with what it'll be close to. I know it'll be close to water, so that would be 4,186 joules per kilogram for each degree Celsius. And so I can't remember exactly what it was for human tissue, but it's very close to that. So forgive my imperfections here. But doing this calculation, I will cancel the unit and get a change in temperature in units of degree Celsius. So this 500, then divided by 8, then divided by 4,186. Whoa. That's way smaller than I thought. I know water has a big specific heat. Maybe I'm remembering wrong here. Yeah, let me take... it's probably worth taking a moment here. Let's see if I can scan this. Okay, so body tissue. Here we go. 3,500. Okay. So that's going to make it a little bit higher. It's not quite as high as pure water. Let me try this again. 500 divided by 8 divided by 3,500 and 0.017 degrees Celsius. Okay. Like that. Better. Okay. Good. And, oh, was there a part D to this? No, that's it. All right. Take care.